Welcome to this video on visualizing entropy. We're going to do that in the form of learning to read Maxwell-Boltzmann distributions. And what we want to start off with here is making sure that you've watched the introduction to entropy video, otherwise this is going to be very confusing. Another reminder is that we're going to be using the Boltzmann definition of entropy. And the Boltzmann definition of entropy is more important and more useful than the standard, very nebulous definition of entropy being a measure of disorder. So do yourself a favor right now and just forget that definition until you really need to use it at a different time. So first of all, I have the Boltzmann definition of entropy up here in the standard equation form. And remember that S stands for entropy. And this is a measurable quantity that's actually very practical, as you'll see in later videos. This term over here is the Boltzmann constant. And the Boltzmann constant, remember, is a number, and it must not be confused with kinetic energy, which this K shares as a symbol. We then have the multiplicity, and I have the multiplicity defined again here as the number of possible microstates for a given macrostate. And that's super important in understanding what we're going to be talking about next. So make sure to go back to the entropy introduction video to get a visual definition for what this is. So let's say I have two different macrostates for the same gas. So I'm going to talk about helium here. So we'll say we have helium, and we have helium at what I'm going to define as macrostate A, and helium at macrostate B. Now, macrostate A and macrostate B are defined by various variables like pressure, volume, temperature, internal energy, and of course entropy. But what I'm going to only focus on here is the temperature. So I'm going to say that we are going to look at the temperature of helium at state A and compare it to the temperature of helium at state B. So the temperature of the helium at state A, I'm going to say is 80 Kelvin, and the temperature at state B, I'm going to make 300 Kelvin. And if you go back to watch the introduction to entropy video, and you look at the idea of the multiplicity of these systems, what we see is that the multiplicity of macrostate A is less than the multiplicity of macrostate B. And the reason for this is because of the movement of the particles within the system. So in other words, what we're saying here is if we write out our definition for temperature, which was the average kinetic energy per particle, or a particle in the system, is equal to 3/2 times the Boltzmann constant times temperature. If we compare that at state A to this equation written out for state B, what we see is that the average of the particle kinetic energy, of course, is going to be the major difference and the reason that we read a different macrostate temperature. So let's go ahead and expand kinetic energy out to the equation that we learned before, which is 1/2 mass times velocity squared, and I'm going to set that equal again to 3/2 kb times Ta. We'll do the same thing over on this side. 1/2 mass times velocity squared is equal to 3/2 kb times temperature B. And what we see happen in these systems of gas is that the average kinetic energy of a particle in the gas at a lower temperature means that there are less variations in the speed. In a higher temperature gas, there are going to be more variations in the speed of the particles. And that's going to be what's most important in learning to visualize what the entropy looks like. So essentially what we're saying here is that the entropy at temperature B is greater than the entropy at temperature A because the multiplicity at macrostate B or temperature B is greater than the multiplicity at macrostate A. So let's look at what that looks like on this graph. And the first thing is to make sure we understand what the axes are labeled as. Well, here I have speed of the particles in meters per second on the x-axis, and on the y-axis here I actually have the probability or the fraction of molecules at that particular speed. Okay, so basically what this is saying is that I have two curves here that are representing where it's most probable to find the speed of that particular particle. So here I have temperature 80 Kelvin, that's temperature A, and over here I have temperature B, which is at 300 Kelvin. And if I compare the two of these, what I'm seeing is that most of the particles in the system at temperature A are moving, it looks like, around 200 meters per second. Now, if we actually solve for the v variable here, it's actually going to be the root mean squared velocity, which is actually shifted slightly to the right. And so what truly is happening here is that we would say maybe most of the particles are moving at 250 meters per second. Now, when I go to 300 Kelvin, what I see is that, yes, the temperature, so I'm going to scoot over here to the root mean squared value, or roughly that. Okay, and I'm going to say, let's say that this is occurring at 475 meters per second. So I definitely can see that the velocity, or the average velocity of the particle, is higher than it is in state A. But what's happened is that there's less of the particles at that speed compared to what they were at state A. So in other words, as the temperature is increased, that means that the average kinetic energy of a particle is higher, or the velocity of the particle is higher, but there's a greater variation if we look at the spread of this particular curve. So this is kind of a statistical curve that says the probability of finding a particle at this particular speed is at this value here. It's a higher value for a higher temperature, but there's more variation in the possible speeds than there would be at a lower temperature. So at the lower temperature, more of the particles are at the same temperature, so there's less variation in their speeds, but they are at a lower speed than over here. So basically what you can do is say that the wider the spread of one of these bell curves, the greater the multiplicity, and therefore the greater the entropy. So what we're going to say here is that if a curve gets wider, that implies that the multiplicity and therefore the entropy are going to be at a higher value than for a less wide curve. Multiplicity and the entropy would be at a lower value. Now, why does the peak increase as I move to the left? Well, if I'm comparing the exact same system here of the same number of helium molecules that obviously are going to all have the same mass, if we're comparing the two, that if I have more molecules moving at the same speed and less variation, so the peak gets narrower, the peak has to go up to represent the same number of particles. So you could say that the area underneath this curve is really going to tell us either 100% probability, or another way of looking at it is the number of particles in the system, depending on what you have labeled on the sides here. So essentially what we're saying is, in order to account for the fact that there's no particles have left the system, that if the system decreases in temperature, that means that there are more particles moving at the same speed, but less variation in the speeds of the particles, which would be the opposite that's happening here at the higher temperature. One thing to note here is that this is not a symmetrical bell curve, and that's why the root mean squared value shifts to the right, is that the right-hand side of the curve is slightly larger than the left-hand side of the curve, but we're not going to get into that in a lot of detail. It's just something to notice. Now, the Maxwell-Boltzmann distribution can be shown in this form, where I'm really looking at the same gas at two different temperatures, but it can also be looked at in this form over here, where now I have, let's see, it looks like 5 different gases, but these are all at the same temperature. And this is an interesting perspective, because what we see here is that when we're comparing average kinetic energy of a particle between two different gases, we now have to take into account that the masses are different of the two particles. So helium has the least mass, therefore it can have the highest average velocity of its particles, and so helium will have a much wider spread or a much higher temperature at the same a much higher multiplicity at the same temperature than will helium, water, and 2O2. And you can kind of see that. So all of these are at the exact same temperature, but their speeds are not going to be the same because of the mass difference of the molecules. And so we can see here that oxygen, diatomic oxygen, at the same temperature as this hydrogen, those two are going to be very different in their entropy amounts, even though they're at the same temperature. So you have to be careful when you're looking at a Maxwell-Boltzmann distribution. You can't necessarily say that a higher temperature has a greater entropy because you have to make sure that you're first comparing the same particles. If you're comparing the same particles, then yes, a higher temperature will have a higher entropy. But if you're comparing different molecules or different kinds of gas at the same temperature, then you obviously a higher temperature does not indicate a higher entropy. As you can see here, these are all at the same temperature, but the hydrogen has a much wider spread of possible values, so therefore a greater multiplicity and a greater entropy than does the oxygen. Now what we're going to do in some later videos is take a look at what are the ramifications of the fact that as you look at what happens to the entropy. As the entropy of an individual gas changes, it's always going to increase or can remain the same. We're going to take a look at that for some of the engine cycles, but those will be considered more advanced topics, so ones that you do not have to achieve to meet mastery in this topic.